Welcome back everyone. Today we're going to be configuring device access control and VPNs. Secure device configuration is a critical responsibility in information technology. Misconfigured network devices can allow unauthorized users to gain access to routers, switches, and firewalls. In many cases, attackers succeed simply because default credentials are left unchanged or administrative access is not properly secured. For this reason, protecting access to networking devices is a top priority for IT professionals. In this chapter, you will learn how to secure networking devices using device access control best practices. You will also explore virtual private networks and how they enable secure communication between remote offices and remote users. Topics covered in this chapter: device access control and virtual private networks. Network engineers often focus on configuring devices so traffic can move efficiently across local networks and between subnets. However, networking devices also store sensitive information such as device configurations, routing information, MAC addresses, and syslog data. If an attacker gains access to these devices, they could perform malicious actions such as modifying routing paths, deleting device configurations, erasing the Cisco iOS image, or manipulating spanning tree behavior. For this reason, securing access to networking devices is essential. In this section, we will examine how to secure physical, remote, and administrative access to Cisco devices. When purchasing a new Cisco iOS device, a console cable is typically included to allow administrators to connect directly to the console port for device management. By default, the console interface has no security enabled. This means anyone with physical access to the device and a console cable could gain administrative access to routers, switches, firewalls, or access points and potentially make unauthorized changes. To prevent this, securing the console port is an essential step in protecting Cisco networking devices from unauthorized physical access. In this lab, you will learn how to secure and enable authentication on the console port of a Cisco iOS router. The following topology will be used in Cisco Packet Tracer. So lab requirements. Ensure the following setup is used. Use a Cisco 2911 router. Connect PC1 to the router using a console cable. The cable should connect RS-232 interface on PC1 and console port on the router. So accessing the router via console. Click PC1, select the desktop tab, and click Terminal. In a real environment, terminal emulation software such as PuTTY, Secure CRT, or TerraTerm would be used to access the console. Now we're going to configure terminal settings. Use the default terminal parameters and click OK to establish the console session. These settings ensure the PC serial interface matches the Cisco console port configuration. The initial configuration dialog will appear. Type No and press Enter twice. You will now see this user exec mode prompt, router. Notice that no authentication was required. This is the default behavior for the console port. So verify current access method. Run the following command, show users. The asterisk indicates the session you are currently using. In this case, it confirms the connection is through the console interface. Now we're going to check user privilege level. Run show privilege. Cisco iOS uses privilege levels ranging from 1 to 15. Level 1, limited user access. Level 15, full administrative privileges. Now we're going to check the console configuration. Enter privileged mode, enable, then run show running config. You will see that no configuration exists under the console line, meaning anyone with physical access could connect to the device. Now we're going to secure the console port, configure a password, and enable authentication. So here we'll use enable, conft, configure terminal, line console 0, password, console pass, login, and exit. So here, line console 0 accesses the console line configuration. Password console pass is self-explanatory, it's set console password. And login, enable authentication on the console port. Without the login command, the password will not be enforced. then verify authentication, reconnect the console session. You should now see a password prompt before accessing the router. Enter the password, in this case console pass, and verify the configuration. Run show running config. You should now see the configuration applied under the console line. In this lab, you learned how to access a Cisco router using the console interface, verify current access and privilege levels, configure a console password, enable authentication on the console port, and verify the configuration using show commands. This ensures physical access to the device is properly secured. Older Cisco devices often included an auxiliary port, which was designed to allow remote management of a router through a modem connection. This enabled administrators to access the device remotely using a command line interface, CLI. By default, the AUX port does not require authentication, meaning unauthorized users could potentially gain access if the interface is not secured. In this lab, you will learn how to secure and enable authenticated access to the AUX port on a Cisco iOS router. The following topology will be used in Cisco Packet Tracer. So here's the requirements. This topology extends the previous lab, securing the console port. Add PC2 to the existing topology. Connect PC2 to the router's AUX port using a console cable. On PC2, open the terminal application. Connect to the router via the AUX port and press enter a few times to display the CLI prompt. You should gain access to user exec mode without authentication, which confirms that the AUX port is not secured by default. Verify the connection method. Run the following command, show users. This command confirms the current connection method and shows that the session is using the AUX interface. Check privileged access, so we'll enter privileged mode, enable, then verify the configuration of the AUX line. By default, privileged access may be restricted depending on whether an enable password is configured. Secure the AUX port. Open a console session from PC1 and configure authentication for the AUX line. So the commands we're going to use is enable, configure terminal, line AUX 0, password AUX pass, login, and exit. Line AUX 0, this accesses the AUX line configuration. Password AUX pass, sets the AUX password. Login, enable authentication for AUX access. Now we're going to verify authentication. Reconnect AUX session from PC2. You should now see a password prompt before accessing the router. Enter the password AUX pass. Verify the configuration. Show running config. You should now see the authentication configuration applied under the AUX line. In this lab, you learned how to access a Cisco router using the AUX interface, verify the current access method, configure authentication on the AUX port, and verify the configuration using show commands. Securing the AUX port helps ensure that remote management access to the device is properly protected. Cisco iOS devices include 16 virtual terminal lines that allow network engineers to remotely manage routers and switches. These lines enable administrators to connect to devices located at remote offices, data centers, or customer sites without requiring physical access. VTY lines support remote terminal sessions using Telnet or SSH, allowing both inbound and outbound connections. Telnet is a network protocol used to establish remote CLI sessions between a client and a server. Cisco devices include a built-in Telnet server that allows administrators to manage devices remotely. However, Telnet is insecure because it transmits all data, including usernames and passwords, in plain text. An attacker who captures network traffic could easily read this information. For this reason, Telnet should not be used in production environments. Telnet uses TCP port 23 by default. Secure Shell is the recommended protocol for remote device management. SSH encrypts all communication between the client and server, protecting credentials and session data from interception. SSH also requires user authentication, typically using a username and password, providing stronger security than Telnet. SSH uses TCP port 22 by default. In this lab, you will configure Telnet access on a Cisco IOS router. The lab requirements: Cisco 2911 router and Cisco 2960 switch. We're going to configure appropriate IP addressing and ensure PC1 can ping the router. Access the router via the console and run show running config. You will notice that VTY lines 0 to 4 allow Telnet by default, but remote access will fail because no password has been configured. Configure Telnet authentication on all VTY lines. So the commands we'll run is enable, configure terminal, line VTY 015, password, Telnet pass, login, and exit. Line VTY 0 to 15 configures all VTY lines. Password Telnet pass sets Telnet password, and login enables authentication. Now we're going to verify configuration. Run show running config. Ensure the password and login commands appear under the VTY configuration. Test the Telnet connection. On PC1, open desktop. Go to Telnet SSH client. Set the connection type to Telnet. Enter the router IP address and click connect. Enter the configured password, which is Telnet pass, and use the following commands to verify the connection. Show users. The output will show the active VTY session and source IP address. Now we will enable SSH on a Cisco iOS device. Because Telnet is insecure, SSH is the recommended method for remote device management. So first, we're going to configure the hostname. So type enable, configure terminal, and hostname R1. Then we're going to configure domain name, IP, domain name, cyberedlabs.local. The domain name is required for RSA key generation. Now we're going to create local user account, username user1, secret SSH pass, and we're going to generate RSA encryption keys. Crypto key generate RSA general keys modulus 1024. Now enable SSH version 2. IP SSH version 2. SSH version 2 provides stronger security than SSH version 1. Now we're going to restrict VTY lines to SSH only with line VTY 015 and transport input SSH. This disables Telnet access. Now configure local authentication with login local and no password. Configure idle timeout with exec timeout 2. This disconnects idle sessions after 2 minutes. And test the SSH connection. On PC1, open Telnet SSH client, select SSH, enter the router IP address, specify the username, so user1, enter the password, SSH pass. You should now be connected to the router via VTY line 0 using SSH. Verify SSH operation, show IP SSH. This displays SSH version, authentication timeout, and authentication retry count. You can also view active sessions with show SSH. In this section, you learned how to understand VTY lines and remote management, configure Telnet access, configure SSH for secure remote administration, restrict remote access to SSH only, verify active sessions, and SSH status. When a user gains access to Privileged EXEC mode, they can view sensitive information about the device and network. From this mode, a user can also enter global configuration mode and modify the device configuration. Because of this, controlling access to Privileged EXEC mode is essential for device security. Cisco iOS provides several built-in features that help prevent unauthorized access to this level of control. Secure boot image prevents a Cisco IOS image from being accidentally or intentionally deleted. And secure boot config. This protects the running configuration file. One way to protect privileged exec mode is with the enable password command. Here's an example. Enable password Cisco123. After this command is configured, users must enter the password when moving from user exec mode to privileged exec mode. However, this method has a majority security weakness. The password is stored in plain text within the configuration file. Anyone who can view the running configuration can see the password. Because of this vulnerability, using enable password is not recommended. A more secure method is the enable secret command, which encrypts the password using a hashing algorithm. Here's an example, it's enable secret. The password is stored in the configuration file as a hashed value, preventing it from being easily read. Cisco IOS uses numeric values to indicate the password encoding type. So type 0, plaintext, which is enable password, and type 5, MD5 hash, enable secret. If both enable password and enable secret are configured, Cisco IOS will always use the enable secret value, since it has the stronger option. Because of this, the enable password should be removed, and you can do this with no enable password. Over time, the MD5 hashing algorithm used by Enable Secret has been weakened by modern cracking techniques. To improve security, Cisco introduced stronger hashing using SCRYPT. SCRYPT passwords are stored as type 9 hashes, which use the SHA-256 algorithm and produce much longer, more secure hash values. When possible, always use the most secure password hashing method supported by the device. Cisco IOS also includes the AutoSecure feature, which can automatically apply multiple security settings, and the command for this is AutoSecure. This command enables the Cisco IOS lockdown feature, helping protect the device from common security risks. So the key takeaway, to properly secure privileged exec access, avoid using enable password, use enable secret or stronger hashing methods when available, remove weaker passwords from the configuration file, and apply additional security features such as AutoSecure. Securing privileged exec mode ensures that only authorized administrators can modify the device configuration. On Cisco IOS devices, some configuration modes only allow passwords to be set using the password command. This includes interfaces such as line console 0, line AUX 0, and line VTY. The password command stores password in plain text within the device configuration, meaning anyone who views the configuration file can easily read them. When the password command is used, the password appears directly in the configuration file without encryption. This creates a security risk if someone gains access to the device configuration. Certain configurations also require plain text passwords. For example, when configuring point-to-point protocol with password authentication protocol on a WAN link, the password command is used for router authentication. As a result, the password is stored in plain text on the device. Cisco IOS provides a service password encryption command, which encrypts all plaintext passwords stored in the configuration, and the command to do this, service password encryption. After enabling this command, any passwords configured using the password command are automatically encrypted. This includes passwords configured under console lines, AUX lines, and VTY lines. Passwords encrypted with this command use type 7 encoding. While this method hides passwords from casual viewing, it is not considered strong encryption and can be easily reversed by attackers. However, it remains the only built-in method on Cisco IOS for encrypting passwords created with the password command. So key takeaway, to improve security on Cisco devices, avoid leaving passwords in plain text, use enable secret for privileged exec access, and enable service password encryption to protect passwords configured with the password command. This helps prevent unauthorized users from easily viewing passwords in the device configuration. As organizations grow, they often open additional branch offices in different locations. One challenge that arises is how employees at these remote offices can securely access resources located at the main office. One option is to replicate the entire IT infrastructure at the new location, but this can be expensive and unnecessary for smaller branches. Another option is to use a dedicated wide area network connection provided by an internet service provider. While this allows offices to connect and share resources, dedicated WAN services often involve significant monthly costs. A more flexible and cost-effective solution is to implement a virtual private network. A VPN creates a secure, encrypted tunnel between two or more devices over an untrusted network such as the internet. Any data sent through this tunnel is encrypted, protecting it from interception or unauthorized access. The benefits of using a VPN is cost-effective. VPNs can use the existing internet connection rather than requiring expensive dedicated WAN links. There's secure communication, all traffic within the VPN tunnel is encrypted, and scalability. Additional branch offices and remote users can easily connect to the corporate network. Many organizations already have firewalls at the network parameter, and most modern firewalls include built-in VPN capabilities. This means a VPN can often be deployed without purchasing additional hardware. Because VPN traffic is encrypted and authenticated, organizations can securely connect branch offices, remote workers, and corporate networks over the internet. Another advantage of VPNs is their support for remote access. Employees working from home or traveling can securely connect to the corporate network as long as they have internet access. Organizations with multiple branch offices often need a way to connect remote locations at their corporate headquarters, where critical resources such as application servers and databases are typically hosted. Traditionally, businesses use WAN services provided by internet service providers, such as Metro Ethernet or multi-protocol label switching, to connect branch offices. However, these solutions are subscription-based and can be expensive, making them unsuitable for organizations with limited budgets. A more cost-effective alternative is to implement a Site-to-Site VPN. A Site-to-Site VPN creates a secure, encrypted tunnel between two networks over the internet. Since both locations already have internet connectivity, no additional WAN services are required. Each site typically uses a VPN concentrator, such as a router or firewall, to establish and manage the VPN tunnel. In a site-to-site VPN, the VPN tunnel is created between network devices at each location, such as firewalls or routers. The tunnel connects the branch network to the headquarters network. All traffic sent between the two sites is encrypted, and traffic within each local network remains unencrypted. This allows users at remote offices to access corporate resources as if they were on the same internal network. The benefits of site-to-site VPNs is cost-effective, uses existing internet connections instead of expensive WAN services. Secure communication, data sent between sites is encrypted, it's scalable, additional branch offices can easily be added, and redundancy can serve as a backup connection between locations. Site-to-site VPNs are widely used by organizations to securely connect branch offices over the internet while reducing network costs. Many employees work remotely from home or spend most of their time away from the office. These users still need access to corporate resources such as file servers, applications, and internal systems. A remote access VPN allows remote users to securely connect to the corporate network over the internet. With a remote access VPN, a secure VPN tunnel is established between the user's device and the corporate network. Typically, a VPN client application such as Cisco AnyConnect Secure Mobility Client is installed on the user's computer. The VPN client creates a secure connection between the user's device and a VPN concentrator, such as a firewall or router located at the corporate site. Administrators can configure remote access VPNs in two common modes. Full tunnel, all traffic from the user's device is sent through the VPN tunnel to the corporate network. The VPN concentrator then forwards the traffic to the internet if needed. This means all internet traffic passes through the corporate network. Security policies can be enforced centrally. Network monitoring and filtering are easier. And then there's split tunnel. In split tunnel mode, only traffic destined for the corporate network is sent through the VPN tunnel. Inbound traffic is sent directly to the internet from the user's device. Advantages of split tunneling include reduced bandwidth usage on the VPN tunnel, lower CPU and memory usage on the VPN concentrator, and improved performance for internet access. Another option is a clientless VPN, which does not require a VPN client to be installed on the user's device. Instead, the user connects through a web browser, and the connection is secured using SSL or TLS encryption over HTTPS. In this scenario, traffic between the web browser and VPN gateway is encrypted. Other traffic outside this session is not protected by the VPN tunnel. Key takeaway: remote access VPNs allow organizations to securely connect remote employees and mobile workers to the corporate network over the internet, ensuring safe access to internal resources regardless of location. Internet Protocol Security is a framework used to secure VPN communications over IP networks. It provides several security features that protect data as it travels across a VPN tunnel. The benefits of IPsec: confidentiality. Confidentiality ensures that data transmitted through the VPN tunnel is encrypted, preventing unauthorized users from reading it. Common encryption algorithms used by IPsec include DAS, 3DAS, and AES. Encryption protects the data from interception while it is in transit. Then we have integrity. Integrity ensures that data sent across the VPN tunnel has not been altered or tampered with. IPsec uses hashing algorithms such as MD5 and SHA. These algorithms verify that the transmitted data remains unchanged. And authentication. Authentication verifies the identity of the communicating devices or users, ensuring that messages originate from a trusted source. IPsec commonly uses Internet Key Exchange for authentication and key management. Authentication methods may include pre-shared keys, digital certificates, username, and password. Anti-replay mechanisms prevent attackers from capturing packets and retransmitting them later to gain unauthorized access. IPsec tracks packet sequences to detect and block these replay attempts. IPsec uses two main protocols. Authentication header provides authentication and integrity for IP packets but does not encrypt the payload. And encapsulating security payload, ESP, provides encryption, authentication, and integrity protection. In most VPN implementations, ESP is commonly used because it provides full encryption of the transmitted data. Diffie-Hellman is a key exchange algorithm used to securely generate encryption keys over an untrusted network. It allows two devices to create a shared secret key without transmitting the key itself across the network. Common DH groups include 1, 2, 4, 14, 15, 16, 19, 20, 21, and 24. Higher DH groups generally provide stronger security. In this lab, you will configure an IPsec Site-to-Site VPN between two Cisco iOS routers. The VPN will allow secure communication between the HQ network and the Router 1 branch network over a simulated internet connection. Use the following setup in Cisco Packet Tracer. Cisco 2911 routers, configure a default route on HQ and R1 pointing to the ISP, configure static routes on the ISP router to reach the HQ and R1 LAN networks, and assign IP addresses according to the topology. I'm going to put all the IP addresses up on the screen for you to follow along, so feel free to pause if you need to. I'll fast forward through the initial IP configuration just to keep things moving, and then we'll break it down together once everything's in place. Now we're going to enable security license. The Security K9 license enables security features such as IPsec, SSL, and SSH. So on the HQ router, if you're not already in configuration, type enable and configure terminal. Then we're going to type license, boot module, C2900, technology package, security K9. Accept the license agreement and then save and reload the router. After rebooting, verify the license with show version. And as you can see, security K9. Now we're going to configure HQ router VPN settings. Create ACL for interesting traffic. This ACL identifies traffic that should be encrypted across the VPN. So in configuration mode, type IP access list extended VPN traffic. Then permit IP 10.10.10.0, 0.0.0.255, 192.168.1.0, 0.0.0.255, and exit. Next, we're going to configure IKE Phase 1 policy. So type crypto ISA-KMP policy 5, encryption AES 256, authentication pre-share, group 5, and exit. Now configure the shared key. Type crypto ISA-KMP key, my IPsec key, address 192.0.2.6. Configure IPsec Phase 2 policy with crypto IPsec transform set, IPsec VPN, ESP, AES, ESP, SHA, and HMAC. Now create the crypto map. You can do this by typing crypto map IPsec map 5 IPsec ISA-KMP. Description IPsec VPN between HQ and R1. Set peer 192.0.2.6. Set transform set IPsec VPN. Match address VPN traffic and exit. Apply crypto map to the interface. Interface gigabit Ethernet 0/0. Crypto map IPsec map and exit. Configure R1 router VPN settings. So create ACL, IP access list extended VPN traffic. Permit IP 192.168.1.0, 0.0.0.255, 10.10.10.0, 0.0.0.255, and exit. Now we'll configure IKE Phase 1. So type crypto ISA-KMP policy 5, encryption AES 256, authentication pre-share, group 5, and exit. And configure the shared key, crypto ISA-KMP key, my IPsec key, address 192.0.2.2. Now we're going to configure IPsec Phase 2 on router 1 with crypto IPsec transform set, IPsec VPN, ESP, AES, ESP, SHA, HMAC, and create the crypto map IPsec map 5 IPsec ISA-KMP. Description IPsec VPN between R1 and HQ. Set peer 192.0.2.2. Set transform set IPsec VPN. Match address VPN traffic and exit. Apply the crypto map with interface gigabit Ethernet 0/2. Crypto map IPsec map and exit. Now we're going to test the VPN tunnel. From PC1, open the command prompt and ping the server. Some packets may initially drop while the IPsec tunnel establishes. After you get a successful ping, run a trace route to verify the path. Traffic should go PC1, router 1, HQ, then server. The packet will not appear to pass through the ISP because it is encrypted inside the VPN tunnel. Now verify the VPN. Check IKE Phase 1 status with Show Crypto ISA-KMP SA. Check IPsec Phase 2 status with Show Crypto IPsec SA. And then view crypto map details with Show Crypto Map. These commands confirm VPN peer address, permitted traffic ACL, transform set, and active interface. In this lab, you learned how to configure IKE Phase 1 policies, configure IPsec Phase 2 transform sets, create crypto maps, apply VPN policies to router interfaces, and verify VPN tunnels using show crypto commands. You have now successfully configured a site-to-site IPsec VPN between two Cisco iOS routers. Now we'll be configuring a remote access VPN. Remote users will be able to connect securely to the HQ network over the internet. Use the following setup: Cisco 2911 routers, configure default routes on HQ and R1 pointing to the ISP, configure static routes on the ISP router to reach the HQ and R1 LAN networks, and assign IP addresses according to the topology. I'll throw all the IP address in on screen now. Pause here if you want to follow along exactly. I'm going to speed through the basic IP setup and we'll break it down together once everything's in place. So configure the static routes. So HQ router, IP route 0.0.0.0 and again 192.0.2.1. Router 1, IP route 192.0.2.5. and the ISP router, IP route 10.10.10.0, 255.255.255.0, 192.0.2.2, and IP route 192.168.1.0, 255.255.255.0, 192.0.2.6. We're going to enable the security license like we've done in the last lab with license boot module C2900 technology package security K9. Make sure you're on the HQ router and it's in configuration mode. If not, type enable and configure terminal. Accept the license agreement, save the configuration and reload the router. After the router loads back up, you can verify the license with show version. Now we're going to configure VPN address pool. Create an IP address pool for remote VPN users with IPN local pool RA VPN pool 10.10.10.100 10.10.10.110. Enable AAA and configure authentication using the local user database. You could do this with AAA new model, AAA authentication login, RA user VPN local, and AAA authorization network RA group VPN local. Now create a user account for VPN access. Username user1 secret Cisco VPN1. Configure IKE phase 1, crypto, ISA KMP, policy 10, encryption AES 256, authentication pre-share, group 5 and exit. Configure VPN client group, crypto ISA KMP, client configuration, group RA group VPN. Key remote access VPN, pool RA VPN pool, and exit. Now configure IPsec phase 2. Create the transform set used for encryption and integrity. Crypto IPsec transform set, RA VPN, ESP, AES, ESP, SHA, HMAC. Configure dynamic crypto map, crypto dynamic map, remote access VPN 100. Set transform set, RA VPN, reverse route, and exit. Configure static crypto map static VPN map, client configuration address respond. Crypto map static VPN map, client authentication list, RA user VPN. Crypto map static VPN map, ISA KMP authorization list, RA group VPN. Add the dynamic crypto map entry with crypto map static VPN map 20 IPsec ISA KMP dynamic remote access VPN. Apply crypto map to interface gigabit ethernet 0/0, crypto map static VPN map, and exit. Now connect using VPN client. On PC1, open desktop, go to VPN client, enter the required VPN connection settings, and click connect. The VPN tunnel will establish between PC1 and the HQ router. Verify VPN connection, run the following command on PC1, ipconfig/all. You should see a VPN tunnel interface with an IP address from the HQ VPN pool. Test the connectivity to the HQ network, ping 10.10.10.10. We got a success, then run traceRT. The packet path should show traffic going directly to the HQ router through the VPN tunnel, bypassing the ISP and R1 routers. In this lab, you learned how to configure a Cisco router as a remote access VPN gateway, create a VPN address pool, configure AAA authentication, configure IKE phase 1 and IPsec phase 2, implement dynamic crypto maps, and verify VPN connectivity from a client device. This configuration allows remote users to securely access corporate network resources over the internet. Summary. In this chapter, you learned how to secure access to Cisco devices by protecting the console, AUX, and VTY lines, implementing secure remote management and restricting administrative access. You also explored how virtual private networks provide secure communication between remote locations. Additionally, you learned how to configure site-to-site and remote access VPNs using IPsec to securely connect branch offices and remote users to a corporate network over the internet. This chapter has introduced key security practices that help protect network devices and ensure safe communication across networks. I hope you enjoyed this chapter. I'm CyberEd, and I will see you in the next one. Peace.